Hi, how you doing? I'm Bob Sorensen. I'm a senior research analyst here at Hyperion, and for the next few minutes, I'm going to give a quick and dirty overview of what's going on in the quantum computing sector from our perspective. So let me just do a quick screen share, and I can bring up the relevant slides. The key here is, as the title says, is what we're really trying to do is explore how quantum computing doesn't exist as an island of computational capability by itself, but really how it can find its place in the advanced computing sector writ large. Now, certainly the promise of quantum computing is substantial. Quantum systems have the potential to exceed performance of conventional or classical computers in areas such as physical simulation, machine learning, and optimization. The key point here, which we won't get into too much, is there are some interesting phenomena at the quantum level, terms like entanglement and superposition, which for key applications can enable significant performance gains beyond what is possible on a classical computing counterpart. And that's really what drives some of these interesting applications and performance potentials. The list of applications that quantum can be applied to does grow longer every day. There's lots of research going on around the world. Compelling new insights are being developed every day. And ultimately, the goal here is this term quantum supremacy, which means the idea of developing algorithms that are virtually impossible to do on a classical counterpart, simply because perhaps the computational requirements may take so long that something that's doable on a quantum computer in a matter of minutes may take on a classical counterpart a time that exceeds the age of the existing universe. So there's goals there about supremacy, but in the near term, there are some significant advantages that quantum gives that doesn't require hitting this quantum supremacy demonstration, but really just demonstrates the capability to offer some competitive advantage over classical counterparts. Indeed, we talked to users that said, if you give me 20x or 30x or 40x computational capability improvements in quantum, that's enough to get me on board. They're looking at competitive advantage. They're looking at basically some important performance gains that don't demand supremacy, but really are just looking at an accelerator mode. In some ways, you could liken this to what happened when GPUs came out. They offered significant performance promises, but for a narrow range of applications. Quantum, in some larger sense, falls into that same kind of realm. The issue with quantum is that there are substantial challenges ahead. There's formidable technical issues in quantum hardware and software. Development is complicated. We haven't even really decided yet what a quantum computer is going to look like from a hardware perspective. Lots of research being done there. Performance gains are not predictable. The timeframes in progress are not something we can say the industry will project gains here this year. There'll be a 2x next year. There'll be a 4x the year after that. Performance will become in fits and starts, and it's not something that you can schedule. There's looming workforce issues. Finding, educating, and placing the right people to work on the various elements of the quantum ecosystem stack is complicated and something that we're going to be dealing with for the next few years at least. All these factors make treating quantum as a stable market complicated. And that's really some of the concerns in terms of the investment community and within the corporate world about how one can look at the quantum computing sector and do risk assessment to decide, is this worth something you want to do from a return on investment perspective, how much faith you have to have in the technology, and what ultimately will be its use case applications and the financial payoffs or the technical payoffs or the national security payoffs in those particular fields. The one thing I really want to stress in all this is that quantum computing research right now is a global activity. This is just a quick summary of R&D publications from leading R&D journals over the last between 2015 and 2019 using a simple search. And the three takeaways from all this are these. First off, you'll notice that there's an awful lot of countries involved in quantum computing research. China and the United States are leaders right now, but Germany, UK, India, Japan, the list does go on and on. This is a widespread research activity. The other point I'd like to make is that the curve on research interest is all positive for these countries. There's more and more research being done throughout the world. And the last point I'd make is that China and the US right now are basically the leaders in R&D development. That's not to say that there are not widespread government programs within quantum at this particular point in time. This is just a sampling of the large government programs that are going on. It's not as if Canada has one funding framework. There are additional programs within quantum within Canada. Same within all these nations. This is just a select idea to give you a sense of the broad scope of quantum computing research and funding at the government level. I want to just give you a quick overview of some of our recent forecast summaries that we did in conjunction with the Quantum Economic Development Consortium, where we ended up surveying approximately 250 suppliers and users of quantum computing to come up with what we think is a substantive and but strong baseline projection of where the market's going. So the bottom line is we projected that the quantum computing market was worth about $250 million in 2019. We're looking at about a 27% CAGR for the next four years, which would drive the market to about 830 million in 2024. On-prem and cloud access hardware will comprise about 50% of the global market for at least the next 3 years. That means the division between users who prefer to put a quantum system in-house, on-premise, or access it through a cloud service provider or some other cloud access model will comprise about 50% of the market. The remainder for things like application software, middleware, and professional quantum services. As I mentioned earlier, optimization, physical simulation, and machine learning are all important, and interestingly enough, they almost near equally divide the application space with about a third apiece. As I said earlier about cloud access models, we firmly believe that user access to quantum computing will primarily be through cloud access at about 3 times the rate of the on-prem option. Our forecast is near-term market ramp up. There's new applications and use cases, not just for traditional HPC, but for the enterprise IT computing environment. The key here, as I mentioned in the beginning, quantum computing is not a replacement for classical, but a companion technology. And the key point here is development is happening in many dimensions and in parallel. At the hardware level, at the software level, we're seeing algorithmic development. We see things like hybrid classical quantum systems where you harness the computational capabilities of supercomputers and use the quantum goodness of quantum systems to attack a single problem in a hybrid environment, and also the emergence of quantum-inspired algorithms, developments in the quantum world that the classical world is looking at and saying, hey, that's something we can do as well. And so we're actually seeing some renewed vitality in the classical algorithm section driven by quantum-inspired capabilities. So that's the quick roundup. As I said, it was a fast and furious take. If you have any additional questions or comments, please respond to the email, get in touch with me. But otherwise, I hope this presentation was useful, and I hope that the rest of your conference proceeds very well. Thank you, and have a good day.